Welcome to EDU World Space.
Potential energy. The potential at any point due to the coaxial cylinders is the sum of the potentials due to each of them. So the electric field at distance r from a straight line of charge is given by this following formula. So if E is equal to lambda over 2 pi times the permittivity of free space times r. So now here lambda is linear charge density, and as I said before, EO is the permittivity of free space. And so the potential at any point, so let's say at point A minus point B, is equal to the integral of A to B of ER and with respect to dr. So now if we substitute the equation here, we're going to get that it's equal to AB lambda 2 pi EOR. And so if we compute this, we're going to get that this is equal to lambda. Oh, sorry, I forgot the dr in this case. So this is dr. So technically all these are constants, so we can move it outside the integral. And if we compute this, we're going to get that it's equal to 2 pi r. Sorry, the r is not there since it's integrated into log over. And if we use the parameters too, it's going to be log b over a. And so this is another equation for the potential. So the potential outside the r is greater than b is a hollow tube of radius b, and the charge per length is negative lambda. So the potential inside of the same hollow tube of radius b and charge per unit length negative lambda is equal to 0. So now to move on to part A, the potential at a distance r, which is less than the radius of the metal cylinder. So we can write it as this: V r. So this is r is less than a, is equal to, as I said before, 0, because the potential of r less than b is equal to 0. 0 plus lambda 2 pi EO, and then this is ln b over a. Sorry, there should be a ln here. So therefore, the potential at distance r is equal to this. If you just get rid of the 0 because it holds no value. So now that's the answer to part A, since this is the potential at distance r. So now if you move on to part 2 of part A, the potential at distance r is greater than a and is less than b. So now let's write another new expression. So r is greater than r. Sorry, let me write that again. So a is less than r, but r is less than b. So at this point, it's just once again pi lambda 2 pi over permittivity times the ln of p over a, and this is plus 0. So therefore, the potential at distance r is equal to this. So this is br, sorry, since we're doing it with respect to r. So, and this is plus 0, but we don't need to include that here. And now moving on to part 3. So the potential at a distance r, which is greater than the radius of the middle cylinder. So let's write a new expression. So this time r is less than b is equal to negative lambda 2 pi times the permittivity ln br plus, so this is a plus lambda 2 pi times the permittivity and once again ln VR. But since these are of opposite values and are the same term, these actually just cancel each other out and it's equal to 0. So now moving on to part B. So at R equals B, the potential is at, so let me rewrite that. At R equals B, the potential of B is equal to pi lambda. The potential is actually equal to 0. And at R equals A, the potential is, so VA is lambda times 2 over 2 pi times the permittivity times ln B over A. So now if you find the potential difference, which is VAB, so it's VA minus B, which is going to be this since VB is equal to 0. So let's just bring that down here. The same expression. So let's bring it down. So now the potential difference is equal to this, and that's the answer for part B. Now moving on to part C. The relationship between the electric field and the potential can be written by this formula. So the electric field is equal to the derivative of the potential over the derivative of R. So if you substitute this following equation up here for B, we're going to get that it's equal to, since this first part is just constant, so we can bring that out of the derivative, 2 pi EO, and so it's D times D of B over dr, and this expression, so it's ln B over A. Let me put that in parentheses. So now if we derive that, we're going to get that it's equal to lambda 2 pi times the permittivity. And if you derive this, it's just going to equal 1 over R. And so from the result obtained in part B, we can set this equal to the result in part B. And therefore, the equation then reduces down to P is equal to VAB over ln B over A times 1 over R. And therefore, this is the answer for part C, and this is the electric field. Thank you.